start with the mechanical model we created in part 1 of this video series. This includes composite materials we imported into our engineering data, the rotor arm geometry we simplified, and the 2D mesh we created. We'll add an ACP system template to our project workflow by navigating to the toolbox, locating the ACP pre-system, and drag it over the mechanical model cell B4 to automatically create shared connections. Update the model before we open it in ACP pre. Our 2D mesh successfully loaded into ACP. Let's review the material data to make sure we have our composite materials that we created in part 1 and shared with ACP. We can see that the engineering constraints are grayed out because they're defined previously in our engineering data. Close this and return to ACP. Now we need to create fabric properties from our composite material data. Right-click and select Create Fabric. For the first fabric, we'll name it Epoxy Carbon UD Wet, and we'll select the material from the drop-down and change the thickness to 0.2 millimeters. We'll go to the Analysis tab and select our engineering constraints, and we'll go to the Draping tab and change the material model to unidirectional. Hit OK. We'll repeat this process for the woven fabric. Change the thickness to 0.4 millimeters. Check our engineering constraints in the Analysis tab and confirm that our material model is woven. We previously created a coordinate system that we'll use here as our rosette. The x-axis defines the 0-degree direction for our composite plies. Now we'll define the oriented selection set, which defines the basis for the layup definition in ACP. Plies are applied on the oriented selection sets and not on element sets. So we'll start with applying the element set all elements, selecting a point on our rotor arm, and let's flip that so the stacking sequence goes in the vertical direction. We'll select the rosette that we created earlier and hit OK. The ply definition can be organized into modeling groups. These groups provide a convenient way to organize composite definitions and streamline the workflow. So I'll start by making a ply. I'll select the oriented selection set we created. I'll give it one of our material properties and change the name. Change the ply angle to 45 and hit OK. I'll create another ply for the second UD ply in our ply stack using the same process that we did previously, but using the carbon UD material property. Again, we'll select the oriented selection set, we'll change the name of the ply, and we'll change the angle to -45. I'll go ahead and create the rest of the plies now. We can check our laminate thickness using the layup plots. We can see we have 16 millimeters of thickness, just as we did in our previous version. We can use our laminate definition to create a solid model, which I'll apply to all of the elements in the model. We now have a 3-dimensional representation of our laminate thickness. From here, we can exit out Composite PrepPost and return to Ansys Workbench. We'll update our ACP model before adding a static structural simulation. Locate the static structural template in the toolbox and drag it to the right of the ACP pre model. Share the data from ACP pre by dragging cell C5 over to our new model cell D4. We have the option of choosing to transfer our solid composite data or our shell composite data. Solid models are generally a little bit larger and more computationally expensive than shell models, but they can describe the behavior of a structure more accurately when out-of-plane stresses are significant. We can go either way in this case, but today I'm going to do a solid composite data. Update the model before opening Ansys Mechanical. From here, we'll repeat the process we did in part 2 and add a fixed support where the quadcopter attaches to the rotor arm. And we'll add a force at the motor mount hole. Again, 5 newtons in the negative Z direction. We'll solve the simulation and start adding result requests. We'll start with total deformation to check to see if it makes sense. We can see the deformation is 27.7 millimeters, which lines up with our analysis from part 2. We'll add our composite failure tool and toggle on SciWu failure criterion, and then evaluate the result. We can see our inverse reserve factor is well below 1, which means this is a viable result. This concludes part 3 of our quadcopter composite rotor arm analysis.